Nenomatica, where mathematics meets YouTube excellence. We will solve a radical equation by following a precise 3-step algorithm. First, we will show the example and read the problem. Quick challenge. Predict our first move. Step 1. Determine the domain by requiring the radicand to be non-negative. Then we show the result and visualize it on a number line. Step 2. Analyze the left side compared to the right side on the allowed domain. We use the facts that x is at least 2 and the square root term is non-negative. Therefore, the left side is at least 2, while the right side equals 1. Hence, the equation cannot hold on the domain. Step 3. Conclude. Since the left side is always at least 2 on the domain, but the right side is 1, there is no real solution. Let us summarize what we learned. We verified the domain first, compared magnitudes next, and concluded by contradiction that the equation has no real solution. Step 1. Determine the domain from the radicand. The expression inside the square root must be greater than or equal to 0. So 1 minus x is at least 0, which gives x less than or equal to 1. Cubing preserves the inequality direction for real numbers. So x cubed is less than or equal to 1. Subtracting 1, we get x cubed minus 1 is less than or equal to 0. Step 2. Isolate the square root term from the original equation. We rewrite x cubed equals 1 plus the square root of 1 minus x as x cubed minus 1 equals the square root of 1 minus x. Step 3. Compare signs of both sides. From the domain step, we know x cubed minus 1 is less than or equal to 0, while any square root is greater than or equal to 0. Therefore, equality holds only when both sides are 0 simultaneously. Step 4. Solve the 0 conditions. X cubed minus 1 equals 0 gives x equals 1. The square root equals 0 also gives 1 minus x equals 0. Hence x equals 1, which is consistent. To visualize, let's plot both sides and see their unique intersection at x equals 1. Example. We will solve the radical equation exactly in the same step order shown in the context. The problem is x to the fourth plus x squared times the square root of x squared minus 1 equals 1. Step 1. Determine the domain of the radicand. The expression under the square root must be non-negative. X squared minus 1 is greater than or equal to 0, which implies x squared is greater than or equal to 1. Step 2. Square both sides to extend the inequality safely because both sides are non-negative. From x squared greater than or equal to 1, we obtain x to the fourth greater than or equal to 1. Step 3. Rearrange the inequality for later sign analysis. From x to the fourth greater than or equal to 1, we have 1 minus x to the fourth less than or equal to 0. Step 4. Isolate the radical term from the original equation. Start with x to the fourth plus x squared times the square root of x squared minus 1 equals 1. Subtract x to the fourth from both sides to get x squared times the square root of x squared minus 1 equals 1 minus x to the fourth. Step 5. Compare signs to conclude both sides must be 0. The left side x squared times the square root of x squared minus 1 is always non-negative on its domain. From step 3, we know 1 minus x to the fourth is less than or equal to 0. A non-negative quantity equaling a non-positive quantity forces both to be 0. Step 6. Solve the simultaneous conditions under the domain x squared greater than or equal to 1. From 1 minus x to the fourth equals 0, we get x to the fourth equals 1. So x squared equals 1. Also, x squared times the square root of x squared minus 1 equals 0. The factor x squared cannot be 0 because the domain requires x squared at least 1. Therefore, the square root must be 0, giving x squared minus 1 equals 0. Hence, x squared equals 1. Thus, x equals plus or minus 1. Step 7. Verify by direct substitution. For x equals 1, the left side is 1 plus 1 times the square root of 0, which equals 1. For x equals negative 1, the left side is also 1 plus 1 times the square root of 0, which equals 1. Both match the right side 1. Therefore, The solution set is x equals -1 and x equals 1. Example: we will solve the radical equation using a domain first argument, then compare the two radicals to show the left side is always negative, and finally conclude there is a contradiction. Step 1. Analyze the domain of the radicals. The square root of a is defined for a greater than or equal to 0. So x plus 1 is at least 0 and x plus 3 is at least 0, which together give x greater than or equal to -1. Step 2. Compare the radicals using the fact that for non-negative numbers, if it is less than b, then the square root of a is less than the square root of b. Since x plus 1 is less than x plus 3, the first radical is smaller than the second radical, so their difference is strictly less than 0. Step 3. Check for contradiction. The left side is always negative, but the right side equals +1. A negative number cannot equal 1, therefore the equation has no real solution. Summary: we restricted the domain, used the increasing property of the square root, showed the left side is always negative, and concluded by contradiction that there is no solution. In this lesson, we will solve a radical equation step by step. The equation is x plus the square root of x squared minus 2x equals the square root of x. Step 1. Determine the domain so that every square root is defined. We need x greater than or equal to 0 from the term square root of x, and x squared minus 2x greater than or equal to 0 from the other radical. Factor the quadratic as x times x minus 2. This is non-negative when x is less than or equal to 0 or x is greater than or equal to 2. Intersecting with x greater than or equal to 0 gives x equals 0 or x greater than or equal to 2. Let's illustrate that on a number line. Step 2. Use the domain to rewrite the equation cleanly. Combine the inside of the second radical. Square root of x squared minus 2x equals square root of x times x minus 2. Because the product under a square root can be split only when each factor is non-negative, we will split into two cases that match the domain. Case A, x equals 0, and case B, x greater than or equal to 2. Case A, x equals 0. Substitute 0 into the original equation. We get 0 plus 0 equals 0, which is true. So x equals 0 is a valid solution. Case B, x is greater than or equal to 2. Now both x and x minus 2 are non-negative. So square root of x times x minus 2 equals square root of x times square root of x minus 2. Substitute that into the equation and factor out square root of x. This gives two possibilities. Either square root of x equals 0 or square root of x plus square root of x minus 2 equals 1. But when x is at least 2, square root of x is at least square root of 2, and square root of x minus 2 is at least 0. Therefore, their sum is at least square root of 2, which is bigger than 1. So the second possibility is impossible. Therefore, the only solution in the domain is x equals 0. The problem is square root of 4 minus x squared equals 500 times, open parenthesis, 3x minus 9, close parenthesis. Our plan is 1. Find the domain where the square root is defined. 2. Compare the signs of the left and right sides on that domain. And 3. Conclude whether a solution exists. Step 1. Domain. The expression under the square root must be greater than or equal to 0. So we write 4 minus x squared greater than or equal to 0. That means x squared is less than or equal to 4, which gives -2 less than or equal to x less than or equal to 2. Let's visualize this interval on a number line. Step 2. Sign comparison on that interval. If x is between -2 and 2, then 3x is between -6 and 6. Subtract 9. 3x minus 9 is between -15 and -3. So 3x minus 9 is always negative on the domain, and multiplying by 500 keeps it negative. Meanwhile, the square root on the left side is always non-negative. Let us overlay a sign chart. We bring the domain line back, mark y equals 0 as a reference, and sketch the line y equals 3x minus 9 across the domain. Notice it stays strictly below 0. Step 3. Conclusion. Could the right side be 0? That would require 3x minus 9 equals 0, which gives x equals 3, but x equals 3 is outside the allowed domain. Therefore, the left side is non-negative, and the right side is strictly negative for every allowed x. The equation has no real solution. Here are the two equations we will analyze. The first, 2x minus 5 equals 100 times the square root of 9 minus 4x squared. The second, square root of 5x plus 2 minus square root of 5x plus 3 equals 1. Let's start with the first equation. The square root requires 9 minus 4x squared to be greater than or equal to 0. Solving gives absolute value of 2x less than or equal to 3, which means x is between negative 1.5 and positive 1.5. Let's visualize that domain on a number line. Next, focus on the left side, 2x minus 5. On this domain, 2x ranges from negative 3 to positive 3. If we subtract 5, 2x minus 5 ranges from negative 8 to negative 2, which means the left side is always negative. Now consider the right side, 100 times a square root. A square root is always non-negative, so the right side is always greater than or equal to 0. A negative left side cannot equal a non-negative right side. Therefore, the first equation has no real solution. Let's analyze the second equation. Square root of 5x plus 2 minus square root of 5x plus 3 equals 1. Notice that 5x plus 2 is always less than 5x plus 3. Because the square root function is increasing, the first root is always smaller than the second root, so their difference is strictly negative. A negative left side can never equal the positive number 1. Therefore, the second equation also has no real solution. Example 1. Solve the equation square root of x to the fifth plus 1 plus x equals negative 1. We first isolate the square root. Move x to the right to get square root of x to the fifth plus 1 equals negative 1 minus x. Because a principal square root is never negative, the right-hand side must be greater than or equal to 0, which gives x less than or equal to negative 1. Also, the radicand must be non-negative. So x to the fifth plus 1 is greater than or equal to 0, which implies x is greater than or equal to negative 1. The intersection of these two conditions is x equals negative 1 only. Finally, we verify. Substituting x equals negative 1 does satisfy the original equation. Example 2. Solve x to the fourth plus x squared plus the square root of x squared minus 1 equals 2. The square root requires x squared minus 1 greater than or equal to 0, so x squared is greater than or equal to 1. From this, it follows that x to the fourth is at least 1, and therefore x to the fourth plus x squared is at least 2. Because the square root term is also non-negative, the left side is at least 2, and it equals 2 only when the square root is 0, and both x squared and x to the fourth equal 1. That forces x equals plus or minus 1. We quickly verify both solutions satisfy the equation. We start with the example label and then show the problem statements in bold orange math. Step 1. Determine the domain. Only the square root demands a non-negative radicand, so we require x minus 3 greater than or equal to 0, which gives x greater than or equal to 3. Step 2. Evaluate the signs on this domain. If x is at least 3, then x minus 1 is at least 2, and x minus 2 is at least 1. Cube root and fifth root preserve sign, and the principal square root is always non-negative. Therefore, the left side is strictly positive and cannot equal 0. There is no real solution. Now problem 2. First, determine the domain of the square root of 4 minus x squared. We need 4 minus x squared greater than or equal to 0, so negative 2 is less than or equal to x, which is less than or equal to 2. Next, factor out the common square root. The left side becomes quantity x plus 3 times the square root of 4 minus x squared equals 0. Apply the zero product property. Either x plus 3 equals 0, or the square root of 4 minus x squared equals 0. That gives candidate solutions x equals negative 3, and x equals plus or minus 2. Finally, check the candidates against the domain from step 1, which was between negative 2 and 2. Negative 3 is outside the domain and is rejected. Both plus 2 and minus 2 are in the domain and are accepted. Example, we will solve for x given that x is greater than 0 and x to the power square root of 2 equals 2. We will follow the exact sequence shown on screen. Step 1. Raise both sides to the power square root of 2 to eliminate the radical in the exponent. Step 2. Use the power of a power rule. Square root of 2 times square root of 2 equals 2. So the left side becomes x squared. Step 3. Take square roots of both sides. Since x is greater than 0, the square root of x squared equals x. Step 4. Simplify the right side. The square root of 2 to the power square root of 2 equals 2 to the power square root of 2 over 2. Therefore, x equals 2 to the power square root of 2 over 2. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. Nenomatica, where mathematics meets YouTube excellence.